All right, so we've got the notes for section 5.4, which deals with estimating population, standard deviation, or variance. So this uses yet another distribution, the chi-square. The table looks like this, which is a lot more tricky to read than the z or the t table because you got two different sides. That's because the chi distribution is not symmetrical, like the t and the normal or the z distribution. So we have a left edge and a right edge that calculate separately, which you notice up here. Talk about chi-squared right, chi-squared left. So we'll have to use the table to find those two values separately. So before we just had t alpha over 2's or z alpha over 2's. But for chi, we can't calculate the error for the left and the right the same way. They are different numbers. So in the table, each critical value of chi-squared corresponds to an area given at the top of the table, and each area in that top row is cumulative area to the right. So this is a little bit different than all the other tables because they have been to the left. So before we go any farther, I'm going to make some notations here. Now, these are the alpha over 2 values, essentially. So these two columns here correspond to 80% confidence levels. This is left value, right value. Use this area to the right. So this column is 90%. This is 95%. This is 98%. And this last one over here is 99%. And they mirror going the other way as well. So this is 90%. This is 95%. This is 98%. And this is, was it 99%? So then we've got our degrees of freedom, just like before, going down the side. And, oops, wrong way. The one other thing that we have to be careful of is, let me note this real fast. Make sure I explain it right. I want to put that on the label, the chi left, chi right. So these values are the chi-squared L's. These values are my chi-squared R's. So these numbers form the right edge of my area. These numbers form the left edge of my area. Okay, sorry. All right, so example 1 down here. So a simple random sample of 22 IQ scores is obtained. So our n value is 22. Construction of a confidence interval for a population requires the left and right critical values corresponding. So chi-squared L, chi-squared R. A sample size of 22, find the critical value, left tail and the right tail. So that's actually how I knew those were. So 95%, you split the remaining 5% in half. So 0.025. That's why this one number here is at the 95% confidence level, because it's half of the remaining 5%. This is half of the remaining 2%. This is half of the remaining, whoops, off the screen, 1%. And then they are mirrored over here. So half of the remaining 1% plus the other 99% that's above it, so on and so forth. Okay, so let's see here. So to do this, so I want my chi-squared values. So chi-squared L, so our n is 22, so our degrees of freedom is always one less than that. So I'm going to go to row 21, just down here. And then the 95% is actually the third column, so 10.283. So would be my left value. My right value, I do the same thing except I mirror it. So row 21, again, all the way across. This column is under the 95%, the 35,479. So that's my value for the R value. So this question just has me looking things up from the table. Okay, so let's go to the next page here. So here's our rules for calculating these things. So just some definitions: sigma, the population standard deviation; S, the sample; n is the number of sample values; chi-squared is the left-tailed critical; chi-squared r, the right-tailed. Variance is always the square of the standard deviation, so same thing here. E's or margin of error, so requirements. Simple random sample. Must have normally distributed values even if the sample is large. So if it's not normal, this formula doesn't work. You have to have a normal distribution. No or ends more than 30 or things like that. Okay, so here's your two equations, whether you're finding the variance or the standard deviation. If you notice, the only difference is this one's squared, that one's not. The squared goes away because I took the square root of everything, which is why these two square roots up here. Now, the one other thing to be careful of is if you look at the bottom here, chi-squared r, chi-squared l, they are actually not in the right place. That formula is correct, but the left edge is used on the right side. The right edge is used on the left side. Just be careful. This number should always be larger than that number. Round off rules, so additional decimal place, so on and so forth. Alrighty, so let's look at procedure here. So you got to make sure you have normal distribution. Use n-1 for your degrees of freedom. Find chi-squared r, chi-squared l. Calculate your interval like this. Now, if you notice, this one does not have us finding an error value because the error would be different on either side, so we don't mess with it. If you want to find sigma, you take the square root, changing chi or sigma squared into regular sigma, and round to one decimal place essentially, or one extra place. So example 2, 22. So our n value is 22. Have a s value of 14.3 because the group of 22, that's the standard deviation, so it's an s, it's not a sigma. Consider the sample to be simple random and construct a 95. So we need our chi-squared L and our chi-squared R, which I believe we just found those numbers in the previous example because it was 22 as well there. 22, yep, and it was a 95% confidence. So this number is 10.283, and this is 35.479, in case you forgot how we got those. So here's my table. Go down to 21. For degrees of freedom means it's n-1. So this value is left under the 95 heading, and this value is on the right under the 95% heading. So estimate of sigma, okay, so we're using sigma. So our formula is actually going to be square root of n-1 times s squared over chi r squared less than sigma, less than square root, n-1 s squared over chi. It's hard to write chi's with, so they look like x's. But, so on the left, this becomes, so n-1 is going to be 21, s is 14.3 squared, all over the right value, 35.479, less than sigma. And over here, we're going to have 21 times 14.3 squared. Doesn't matter if the squared's inside or outside the parentheses, it's fine. And this is 10.283. So let's see, 21 times 14.3 squared divided by 35.479, and the square root of that number is 11, pretty much 11. It's 11.002, so we'll call it 11. 21 times 14.3 squared divided by 10.283, take the square root. This comes out to be 20.4. So these are our boundaries for our 95% confidence interval. So if we repeat this process over and over again, 95% of the time, our sigma values will fall essentially between those two values. So, yeah, and I believe that then brings us to the end of the section. So this one's relatively short, but that's all for this.